Good afternoon, and it's always my distinct pleasure and honor to welcome today's speaker, Arlin Krueger, one of our early luminaries of atmospheric ozone studies here at NASA Goddard. Of course, some of you may not know, Arlin was here in 1969, and there are so many people who were not born by then. So he's been here for a while. And he left in 2000, of course, went to UMBC, and then the rest is, he's going to tell us all that story. And he is famous for several balloon, rocket, and satellite techniques, including locator ozone sodes and the TOMS, which is a total ozone mapping spectrometer. Nikolai Krotkov, Arlin's junior colleague from Atmospheric Chemistry Dynamic Lab, who was inspired by Arlin's work, is going to introduce him today. Now, please give me let's give him a round of applause to welcome Nick Krotkov.
Yes, I want to say a few words about Arlin, who actually is responsible for bringing me here, not just at Goddard, but to the United States. I first met Arlin in the early 90s when I was a young postdoc at Moscow, Russia Central Aerological Observatory. I was just defending my PhD in a different field and just changed my field and started working on the joint meteor-free TOMS project, which was launched in August 1991. And my organization, my boss at Central Aerological Observatory, was a Russian counterpart to the Goddard team, which worked on meteor-free TOMS project. I was probably one of the youngest and really hasn't done much work before. But my boss asked me to write very short proposals, what I want to do in my postdoc, and whether I want to come visit United States. So I written a couple of proposals, and that someday my boss invited me to meet US delegation who came to Russia after post-launch meetings. And we came together, and that's how I met Arlin for the first time in Moscow. And I think Arlin asked me whether I want to work on the volcanic eruptions and sulfur dioxide, which I knew nothing about before. And that was kind of very critical decision in my life and completely unexpected. So that was completely new field for me. And later on, I get official invitation for come to here as a visiting scientist for a year from Arlin, and I agree, and that's really cardinally changed my life. So I come to Goddard, and I work with Arlin in winter 1993, and since that time, work really very closely with Arlin. Arlin was my mentor here, not just in the science field of this volcanology, satellite volcanology, but also becomes really a personal friend and personal mentor, develop a really very close relationship. So I remember when Arlin was driving me around here when I didn't have a car, Arlin introduced me to the scientists at Laboratory for Atmospheres. Then later on, and even was driving me to give him some furniture. I rented an apartment, there was nothing there. And I was getting furniture and getting to know all these wonderful people who works at Goddard Laboratory for Atmospheres. And later on, since I was mostly working not on ozone, but on the sulfur dioxide and volcanology, Arlin introduced me to the volcanology people at Goddard. I remember Lou Walter and Charlie Schnetzler. We have weekly meetings together. It was really, really very interesting group between the labs. And I was just, my career was developing with close collaboration with Arlin. Even when Arlin retired from Goddard to UMBC, I worked with Arlin about almost 10 years at UMBC. We have a volcanology group there. And when Arlin really retired after UMBC, I was hired here at Goddard in the lab to continue Arlin's legacy in measuring the volcanic gases clouds with satellites. And we now can measure even pollutions. We can even measure, have so sensitive instruments, we can measure the pollution sources as well. I think this is all started by Arlin, and but today I understand his talk will be about ozone, not about the SO2. So I just rather give time to Arlin to his talk.
Why don't you measure ozone? Those are the words of my graduate school advisor back at the University of Minnesota. And they changed my life because I had been stuck on this quantum mechanics, particle physics course and into boring nuclear physics. And here was a diversion into geophysics. I didn't know it at the time, but that was a major event in that in geophysics you have all the aspects of discovery, of exploration, travel, excitement, you know, nothing more exciting than watching your rocket blow up with your instrument on board, except when your rocket actually flies and makes it up to the mesosphere and you get measurements from it. That's the most exciting thing. So I found that it's such a diverse world in geophysics, at least exploration geophysics, because where else, in what other field could you get a ride on a Hurricane Hunter aircraft at wave top heights into a Category 2 hurricane, but in geophysics? Or where can you get a launch from a secret Soviet ICBM base and be present at the launch? I mean, this is excitement. I advise any young people, geophysics is the field. Well, first I want to talk about my family. I came from Germany, actually from before the German Empire was established in 1871. My great-grandparents had emigrated from the province of Pomerania, Pommern, up here along the Baltic Sea coast. And it was in 1857 when they picked up, lots of people were emigrating because the land of opportunity was America. And many Pomeranians were going to Wisconsin, so the family followed them. The family had 4 boys and 1 girl. Well, this was an interesting time because 4 years later, the American Civil War started. And my grandfather volunteered for the 7th Wisconsin Infantry. And I didn't know much about that until I found out that he was in the Iron Brigade of the Army of the Potomac. Well, this was a famous brigade that was named in the Battle of South Mountain because of their bravery. It was mainly, you know, the frontiers people from Wisconsin and Michigan that were in this brigade. Well, anyway, so I found this book. I was given this book about the Iron Brigade, and I found that there are at least 20 books written about the Iron Brigade. So I know, for one thing, I thought I was the first member of my family to live in the Washington area. Well, no. Actually, he was here for 4 years during the Civil War. So he's the first Washingtonian out of my family. So he was in the Battle of South Mountain, Antietam, Gettysburg, Fredericksburg, Petersburg, and he was even at Appomattox when Lee surrendered. So he saw the whole works. After the war, he went back to Wisconsin, got married, and then veterans were given homesteads, so he established a homestead in Minnesota, and that's where my family continued. So I was born on a farm in central southern Minnesota during the Great Depression. This is a rural community, and a one-room schoolhouse is what we had. And this is a picture of my class, excuse me. My class in the one-room schoolhouse, that's me, and here's my older brother. Well, the things are not good in the Depression, and in fact, my father lost the lease on his farm, so he had to move to a town of Redwood Falls, big town, 5,000 people. But a great place, good schools, and that's where I learned about science. And I learned the scientific method where you can establish truths that are based on logic and on experiment and all of that, and that was my field. So my brother and I were the first of the family to go to college. I went to University of Minnesota, and with the support of my parents and scholarships. Well, at University of Minnesota, I ended up with a bachelor's in physics in 1955, and applied for grad school at Iowa and also at Minnesota. Well, accepted in both, but I decided to stay at Minnesota, and that's where my advisor, Ed Nye, who was famous for nuclear physics, said one day, why don't you measure ozone? And it turns out this was in the IGY. And he had bought some Petzold ozone sondes. Petzold was a German researcher who had designed this ozone sonde to work on balloons where you measure ozone with a filter photometer, looking at the amount of light from the sun versus altitude at an absorbed wavelength. And in order to avoid pointing it, he built this integrating sphere. Now, the other thing Minnesota was doing is the Skyhook balloon program. They were developing these high-altitude, constant volume balloons. So this worked out great. Ed and I knew that I could go learn to fly these balloons and learn how to measure ozone with an optical technique. So that's how I got started, and that's why those words really changed my life. Well, by 1958, most of my fellow students had bailed out, and I could see I was not getting any place, so I went out looking for jobs. And in fact, I got job offers from NASA. NASA was just being formed. Maury Dubin wanted me to come work on micrometeorites. I also got this offer from the Naval Ordnance Test Station in California, China Lake, where they wanted me to set up a balloon program and continue the ozone measurements. Well, it was winter in Minnesota, a cold winter. Guess what I picked? California instead of the East Coast. Not a bad idea, it turns out. So here's China Lake, the high desert, isolated. Beautiful spot, though. It turns out the lab had a long history of research in geophysics, including airglow measurements. It was a very remote site without contamination from city lights. So an airglow observing program was set up out there. In fact, it was well enough known that Sidney Chapman and Marcel Nicolet even came out there in meetings where they planned the IGY. Well, my projects were, of course, the Skyhook balloons, but also ozone measurements. And it turns out I had an opportunity to measure ozone with a satellite very early, and I'll tell you about that. And then I ended up actually with support to the BUV satellite program. In 1960, a fellow from UCLA, Venkateswaran, we called him Venki, of course, came to us with this idea saying, well, we've just launched these echo balloon satellites, and if we could measure the light reflected from that satellite as it goes into the shadow in an ozone absorption band, we could probably measure the ozone profile. So indeed, we had the airglow photometers, and we had tracking mounts, we could track things. So we managed to get some filters in the Chapuis bands of ozone and set out to measure the light from the balloon. And sure enough, we managed to come up with a number of ozone profiles. And here are two of them, and they're compared with the only direct measurements of ozone in the upper stratosphere, and that was by NRL back in the V2 rocket days. So what we saw was reasonable agreement near the ozone peak, but we saw a secondary maximum. Well, these were taken by definition at sunset. So at that time, it's credible that the atomic oxygen was now converting over to ozone, and that's caused the secondary peak. So the other project was derived from my Petzold balloon ozone sonde work, where the Navy, Office of Naval Research, had planned to was building a rocket version of the Petzold instrument, and they had given the contract to Physical Sciences lab in Las Cruces, New Mexico. The engineers did a great job of repackaging this balloon ozone sonde and into a rocket package. They, ONR asked me to review this for technical capabilities, and so I did, and I found that they were using the same filters as the balloon instrument. Of course, you could measure ozone up to the top balloon altitudes, up to 30 kilometers, but it was saturated beyond that. So I said you have to have a couple of shorter wavelengths with higher ozone cross sections in order to extend the measurements up to 60 kilometers. So to make this long story shorter, ONR asked us to take over this program, and that's how I got into rocket ozone work. So we developed this instrument, and it had the same integrating from the sphere from the balloon. It had a filter wheel and all of that, and the rest of this is telemetry. And then we arranged a long lanyard to get us down far enough below the parachute so that it wouldn't block the sunlight. Well, we launched these from Point Mugu, and this is an example of an Arcus launch. The first flight we made was almost successful. Everything worked just right, except we screwed up on the modulation level on the transmitter. We could not recover the data from that. So, well, we knew how to fix that. So we went back and corrected the problem, came back to Point Mugu and launched it again. The rocket blew up. This continued on for the next 11 flights. We never could get, there was always something that went wrong. Finally, on our 13th flight, everything worked, and we got data, and that was it. Close one. Thank you, Navy, for being that understanding and letting us continue. Anytime nowadays, your program would be canceled long before we ever got there. So we looked for opportunities, and the next opportunity up was a NASA-sponsored mobile launch facility cruise along the west coast of South America. The cruise started from Hampton Roads, sailed down through the Panama Canal along the west coast of South America all the way to 60 degrees south, launching rockets. There were aeronomy experiments, a whole bunch of experiments. My plan was to launch rockets every 10 degrees of latitude and get a latitude profile of the upper level ozone. We also had purchased a Dobson spectrophotometer, so we brought that along. So now we were able to measure the total ozone along the entire course, in addition to the upper atmospheric profiles. So here's our results. This is the first latitude survey of total ozone. Now you can do this with a satellite in a few minutes, but in those days it took us 2 months. But nevertheless, here's, we could see the total ozone from 40 degrees, 38 degrees north, dropping down to the equatorial minimum and then up to the mid-latitude maximum in the southern hemisphere. Meanwhile, we were launching rockets, and our first launch at 4 degrees north was successful. The second one at 3 south was successful, but then a string of failures, 1, 2, 3, 4 failures, including one where the rocket, which was on the fantail, the launcher was on the fantail of the ship, the rocket couldn't even make it over the deck into the ocean, so it lay there on the fantail of the ship burning. And the other rockets were all stored just not far from there. So anyway, so here we go. We had, these are the ozone mixing ratio profiles that we got from those flights. And the equatorial profile had a mixing ratio peak down near under 10 millibars, near under 30 kilometers. But as you went up in latitude, the mixing ratios peak increased. And it's the first evidence that there is something going on in terms of the upper level ozone. Well, we got back from the cruise, and at this point, Charlie Barth at University of Colorado had built a scanning UV spectrometer for the OGA 4 satellite. And this instrument would look down at the Earth, and he said we could retrieve ozone if we knew the calibration of the instrument. Well, they didn't have any way of measuring the response of the instrument to extraterrestrial sunlight, so they asked us to provide rocket data on the ozone profile that they could now use in a radiative transfer model to back out the calibration of the satellite. And so we went off to Barking Sands, Hawaii, and got 5 ozone profiles, all very similar. And then Gail Anderson at this time was doing the analysis of the OGA 4 data. So she backed out the calibration, and sure enough, here's agreement between the satellite and the rocket, at least in the middle levels, deviations at the end. So that's the first calibration of a satellite experiment that we had done. Now, also, Ernie Hilsenrath at the time was measuring ozone on rockets using a chemiluminescent technique. And we got together and decided we'd do a comparison. Now, there can't be 2 more dissimilar techniques to measure ozone than chemiluminescence, a local in situ measurements versus the absorption of UV sunlight. But here's what we got, just an amazing correspondence in the mixing ratio between the 2 techniques. So we figured, man, we must have it, we must understand it. Well, my career at China Lake ended soon after that. We were in the Vietnam War, and the Navy decided there is no need for non-directed research. And of course, measuring ozone didn't contribute a lot to the war effort, so they invited me to leave. Well, prior to that time, Don Heath had been building the BUV at a Beckman Instruments company in California. And one of the requirements is that stray light rejection had to be in 6 orders of magnitude. So how do they verify this? You could take it out and point it at the sky outdoors with sunlight. But who wants to take a satellite flight instrument out in the Los Angeles smog? So they asked if they could come up to China Lake, where the air is clear and the sky is clear and everything's nice. And the instrument was brought up, and that's how I got involved in the BUV program. So the result is they found this 6 order of magnitude rejection by scanning from the totally absorbed UV into the fully scattered UV. Well, here's my second career. I went to Goddard, and Don arranged to hire me under a contractor conversion program in 1969, where I was, what I had to do was serve as a technical officer for the BUV during its last year before launch. And in fact, that's a job I really enjoyed because it was close to the satellite instrument. And I'll talk more about the BUV later, but in addition, he wanted me to bring the Rocco's instruments to do validation. And then, of course, we wanted to continue the collaboration with Ernie. The Nimbus 4 BUV was an exceptional instrument. Don Heath is a master in spectrometer design. He worked with Bill Fasty up at Johns Hopkins, did a beautiful job. But the whole technique that the BUV used was proposed by Jitendra Dave and Carl Mateer. And they proposed that they could build an instrument to measure the ozone profile, a dedicated instrument, not just a generalized scanning instrument, but dedicated, and just pick the right wavelengths and everything so you can optimize things. In addition, they had worked out a technique to measure total ozone from space but that required a different kind of a model. The total ozone, of course, you have to look down at the atmosphere that's multiply scattered, whereas the profile retrievals, you could use single scattered light. But they built the instrument so that we could test out that technique. So Beckman was the instrument contractor, and some of you may know Burt Roeder. He's still around. He was throughout this program a great instrument builder. So in the algorithms, Dave did the forward modeling. whereas Carl Matier did the inverse modeling. So that's the team that did the algorithms. Well, so BUV and Nimbus 4 launched on April 8th, 1970. And, well, there was an interesting thing. You know, all the money had been spent. This is a classic thing in the early parts of the NASA that you start out with a budget, and the budget would have money for data processing. Well, you know how things happen. Delays, overruns, all that money disappears. Well, that happened with this program, and in fact, Nelson Spencer, the division chief, didn't believe the instrument would ever work, so he didn't worry about it. Well, but he managed to come up with $20,000 for our satellite data processing. That was our budget. So how was I going to get this done on 20K? Well, you go out and hire grad students, part-time. And that's what I did. And, well, we picked up a few grad students who have moved on from this lowly task. People like Sharad Tak and Ashok Kavishwar and Om Bahiti over here. These people all worked on BUV data, and that's how they got started. And as many know, well, Sharad Tak has moved into the stratosphere of business and all of that, starting SASC Corporation. Ashok became the president of STX and then moved on to the Department of Transport. Om here has started SSAI, and a very successful company that still supports our branch here. So then the other task was the profile validation, which I took over. So we had to validate the data, and so I took rockets out to Point Mugu, California, and here's an example of one of the first validations. This was, you know, what, 2 months after launch. And now the rocket and satellite are totally independent. I'm not calibrating the satellite. The satellite is built with its own calibration using a diffuser plate. And so this, another case of amazing agreement between rocket and satellite. And in fact, Carl Matier retrieved the satellite ozone profile with this algorithm that assumes single Rayleigh scattering and showed the effect if you include a wavelength 2975. Back in those days, we worked in angstroms, by the way, 297.5 nanometers, and showed that if you include a multiply scattered wavelength, it really draws down the profile. You get errors. Okay, how about total ozone? Well, there are Dobson stations all around the world. What we did was pull together all of the Dobson measurements under that the BUV had passed over and compared them to the BUV retrieval. Well, heavens, look at this. We got reasonable agreement from less than 200 Dobson units to over 500 Dobson units. Really another a major step forward. This, of course, has continued on in the years, and we're still working on this, but that was the first demonstration that we could do this with the BUV instrument. Well, in August of 1972, Paul Crutzen called me up and said, look, Arlin, there's been a solar proton event, and the modeling I'm doing of NOx effects on ozone say that the proton of the suitable energy would produce enough nitric oxide to destroy ozone in the upper stratosphere. And, but of course, only where protons could penetrate, and that's in the auroral zone above the geomagnetic cutoff latitude. So I got our team of data processing folks to crank up some orbits, and in those days, we looked at data with big printouts. And so we got the suitable days, took it into Dawn. We looked at this, and we could see the ozone as the satellite went along, heading north, and just at the cutoff latitude, bingo, it dropped by 20%. So that was the proof. And in fact, this is a plot of the ozone in the versus time. This is what, a couple of months. The event is at this time, but here's the change in the polar latitudes. Mid-latitudes, only this. Tropics, nothing. So this was the signature of NOx chemistry in action. So I called up Paul and said, well, you know, Paul, yeah, we found something. You said the ozone was going to go up, didn't you? I didn't get any response. I said, no, Paul, it dropped 20%. So that's how science happens when it's good. About the same time, the French were still setting off nuclear weapons in the South Pacific, atmospheric tests, and we tried to find a case where we flew over a nuclear bomb test, and the bomb should produce nitric oxide, which should destroy ozone, you know. So we found that, you know, a satellite orbit looks kind of like this. You get traces of data from pole to pole and nothing in between. Well, on only one occasion did we overfly a cloud, and it turns out the ozone was changing for other reasons as we went along, so we could never pin down what the bomb effect was on the ozone. Well, that's when the moment of inspiration happened. Look, if we had an instrument that looked on each side of this point of vent, then we could know exactly what happens, and that's where you need an ozone mapper. That's where it started. Fortunately, Nimbus G was opening up proposals, and Don submitted a proposal for an improved BUV, and I submitted a proposal for a total ozone mapper, where we'd do cross-track mapping. We'd get contiguous global coverage at the equator so that we were sure we didn't miss anything that lasted longer, at least a day. And we got the best ground resolution available based on the bandwidth available to us, and that was like 50 kilometers. And I thought that would be good enough to map out jet streams and things like that. Well, Bill Nordberg said, hey guys, there's no way you're going to get two UV instruments accepted on this Nimbus satellite. And so he said, why don't you combine them together? And so there was the SBUV TOMS instrument that shared common electronics and shared a diffuser plate. Well, so with that proposal in and accepted, Paul Crutzen called me up and said, why don't you come back to school and get your PhD? Gave me the choice of going to University of Colorado in Boulder or CSU in Fort Collins. I thought about it and decided, well, if TOMS is going to give some meteorological information, I ought to know something about meteorology. So I picked CSU. And Paul would come up there and work with me he was on chair of the committee with Tom Vonderhaar and George Reed and some others. Well, Paul had some other students at the same time. You may have heard of some of these. Susan Solomon, Jack Fishman, Bob Chatfield were all students of Paul at the same time. And they've gone on to grander things. Well, so I used Paul's photochemistry and got into modeling, which is strange for an experimenter. But instead of trying to calculate what the ozone should be, I calculated what would happen if I prescribed the ozone profile from my rocket data, and then calculated what NOx ought to be. So I had flights, different latitudes, different seasons, and all of that. So in the dissertation, I worked out exactly the variability in NOx. And one thing that I found was in the polar regions, there just wasn't enough NOx around to put the ozone in steady state. And in fact, if you needed thermospheric nitric oxide to be transported down in the polar winter in order to balance out the chemistry. Back to Goddard in 1978, just in time for the SBUV Nimbus G launch. And TOMS worked. And here is the very first image of ozone, total ozone, that anybody has ever seen. It showed structure in total ozone, and instead of, before you used to sit on the ground with a Dobson instrument and watch the ozone values versus time. This explains why the ozone varies versus time. But what you see is there's more information than just total ozone. There's information about the atmosphere in this, and that started a whole new direction. For example, here's a North Pole plot of ozone, and you see features like troughs and ridges that are on an upper air chart. You'd see those as geopotential height variations. You see gradients, you see everything that's going on in the upper troposphere. And in fact, we could pin this down to upper troposphere modulation. It's not what was happening in the stratosphere, but it was happening at what's happening at the tropopause and the upper troposphere. That was important. So I took this to some meteorologists that I know, Mel Shapiro, for example, out at NCAR. He said, well, look, we can nowcast the weather just with a Tom's map. And in fact, we wrote a paper on this. You can see all the upper air systems, you can see all the jet streams. And in fact, Mel found another jet stream, the polar front jet stream, from the Tom's data. Now, Chris Davis then came along and said, well, I bet we could estimate winds just looking at the ozone gradient. So he built a dynamic model using ozone gradients to constrain this and worked out winds. Well, so that's the connection to meteorology, except for one thing. Louis Uccellini was here at Goddard, and he's now head of National Weather Service. But while he was at Goddard, he was working on severe storms. And in fact, the President's Day storm of 1979 was unpredicted. The thing came as a total surprise. It wasn't in the forecast models. So I showed Louis the Tom's data, and he could see way upstream, a couple of days in advance of this storm, this little kink in the jet stream. And that propagated, and by the time it got to the east coast, it blew up, and we had this bomb of a storm. And so Louis knew that if we had the information in Tom's maps, you could do better forecasting. Another area of interest was aviation, where Dan Soa and Northwest Airlines, they had a problem with cabin ozone. And I showed them if they had Tom's maps, they would know they had to either fly under the tropopause in these certain regions or do some other tactics in order to avoid getting the stratospheric rich, ozone-rich air into the cabins. In addition, of course, you could fly an airplane with maximum fuel efficiency just by following the jet stream. But the data couldn't arrive a year later. They had to be in near real time. So we went through a lot of effort to process the data in near real time. And then the trick is, how do you get it out in the field? Remember, these days there wasn't any internet, there wasn't any color graphics, nothing. So we came up with a way of plotting the data using character symbols that would show the patterns. And you can see the ridges and the troughs and all of that in these printer maps. And that's what we used to send out to Northwest Airlines. And they could use that as guidance for their flight planning. Well, so is total ozone meteorological variable? The general circulation models, I tried to validate my concept by looking at general circulation models, but the features didn't line up. The troughs and the fronts were in a different spot than what it showed in the ozone, so I couldn't validate it. So I went to Yale Mintz and Milt Halem. Now, Yale Mintz is one of the developers of general circulation models. And he acknowledged that the forecasts are messed up because the models don't get the positions right. And they both agreed we should try to bring this into models. The problem is a perturbation that large would always cause the model to crash. It just would not work. So to answer the question, no, total ozone is not a meteorological variable. But then something else happened. The ozone hole happened. And here's another whole story. There's another hour's talk on this, but which I'm not going to go into. But a lot of people are key to all of this and understand this very well. There was a problem. We didn't recognize that this was a true event at the time because I had given limits to the ozone processing team on what the lowest and highest ozone amounts would be wherever observed, and they put some margin on there. And if anything was below that, it got flagged and tossed out. So they found all of this flag data down at the South Pole, and because it was out of limits. So they tried to get a confirmation of this from ground stations. Well, even the South Pole had data taken at extremely high solar zenith angles, and Walt Comer, running that station, didn't believe the data when it said it was really low. So that's how we didn't have enough confidence in and that we understood how to do the total ozone retrievals right at the terminator. So other people get the credit for first publications of this, but at least PK got out there, presented the first Tom's maps of this, and Rich Stolarski and et al. Published the first paper on this. The whole Antarctic ozone thing is a unique case where it's really the first collaboration I know of between ozone experimenters, between lab chemists, modelers, environmental activists, and industry. Everybody got involved, and you know, they always used to be isolated fields, but this is a unique case. But the whole thing did generate new entrepreneurial opportunities. For example, you can go out and buy ozone protective clothing. This field has matured, and now you have many websites where you can look at the ozone every day and all the statistics, get videos. This is really a mature field, and there's a lot going on. My question in 1985 is what happens after Nimbus 7 Toms dies? So I went to Shelby Tilford and offered some possible spacecraft we might fly, and he said, well, there's no AO, there's nothing in Earth Sciences for no opportunities, but you need a peer review, so why don't you propose for the SMEX, Space Science SMEX program? And if you can get good reviews over there, then I can justify putting money into building Tom's instrument. And sure enough, we got good reviews, and so we got started building Tom's instrument. We needed to fly them, so we proposed for a Space Sciences Technology Initiative mission called Earth Probe to launch in 1994. We also proposed to fly on the Japanese ADIOS mission for a 1996 launch. However, this was 1985-86 period, and Reagan and Gorbachev, you know, things were changing in the Soviet Union where the old leadership had died out, and Gorbachev was now in charge. And we had Reagan on this side trying to force the Soviet economy to collapse, but he recognized that we can build cooperation between the countries would be to everybody's advantage. One of the things was, let's try to do a joint satellite mission with the Soviets. Well, what do you propose from the US? Turns out Tom's had a reason to fly. Tom's was old enough, so it didn't offer any tech transfer issues, and everybody wanted to do it. So that's the origin of the Meteor 3 Tom's mission. Some challenges here. No precedents, no protocols. We had no idea how the Soviets built spacecraft. We didn't know how they did thermal work. We didn't know anything. But the mission turned out to be run out of Earth Sciences rather than Goddard projects. We were a lot more flexible in Earth Sciences than the projects people could have been, because they never would have tolerated the practices of the Soviets. Totally different. So we started meetings in Moscow in 1988, and NASA and the Hydromet, their counterparts from the Hydromet, had to define which satellite, what the interfaces were, what the integration facility, where would we do the work. The plan was to have U.S. engineers come over there and work within their factories that are secret at the time. and then what launch vehicle and what range. And everything had to be constructed out of, raw cloth, So Shelby Tilford and Sam Keller and Chuck Cody from Goddard here and George Essenwein were the ones that sat down with the Soviets and worked out the details in a series of meetings lasting a couple of years. It was successful. It worked. We managed to do the integration. We managed to work all the problems and design an interface that would match their stuff with our stuff. And also we found a flight memory that we could fly because their memory capacity wasn't big enough for us. But anyway, so Chuck Cody was the project manager, John Liacano, the technical officer, and I was the instrument scientist. Well, we had a successful launch from Plesetsk. This is the secret ICBM base where the Soviet space program started out, really. We launched on the day we had picked 2 years earlier. We launched within 400 milliseconds of the time I picked 6 months earlier. Incredible. You can't do that in the States. Well, also in the States, you can't go stand alongside a rocket to be launched in an hour or so. That's fuel. This upper stage is fuel. But we could all stand around having our pictures taken, hanging onto the tail fin and all of that. Different style of business. Different style of business. But we launched. It was successful. And it, in fact, lasted, continued our database now. After the Nimbus failed in 1992, Meteor 3 toms carried us through 1994. Then Earth probe toms we planned to launch in 94, and it would have been perfect to carry on. But unfortunately, Orbital Sciences has had problems with its Pegasus rocket. A couple of failures set us back 2 years. In fact, it set us back to the time that Adios Tom was planned to be launched. So, we had 2 in orbit at the same time, and so we had to do some fancy footwork on how are we going to manage this. Anyway, the Adios had a massive power failure when the solar cells became disconnected from the spacecraft less than a year after launch. So we lost that excellent source of data. Well, so we went ahead. Rich McPeters and the others all worked on getting another launch called Quick Toms, and built up. We had one more Toms instrument remaining, so we launched Quick Toms in December of 2001. That was supposed to carry on. Well, another Orbital Sciences rocket, Taurus, dumped our satellite in the Indian Ocean. And so that was the end of the TOMS program. That's it. But at least Earth probe lived on until 2006. Well, then I started my third career. I actually was transitioning over to sulfur dioxide because in 1982, PK brought some data to me, a total ozone data showing a big anomaly over Mexico, and asked if I could figure out what was going on. So I knew that their El Chichon had erupted, and I looked at all the volcanic gases that might absorb in the ultraviolet. There was only one that really could match what we were seeing, and that was sulfur dioxide. Holy cow, we could measure sulfur dioxide with Tom's instrument. We could map it out. Never thought of that. Well, it took a new algorithm in order to discriminate the SO2 from the ozone. And in fact, we had enough information to do it. So now, what we could do, we could actually measure the size of volcanic eruptions. These things, volcanic eruptions do have effects on the climate. And people had estimated the size of the sulfur dioxide, which is the climate active agent, by looking at the rocks on the ground and measuring how much deficit there was in the tephra, and saying, well, that's how much sulfur dioxide is up there. Well, we could actually measure it. And in fact, what we found in certain types of volcanoes, explosive eruptions, there was a lot more sulfur dioxide than could be accounted for by this tephra loss data. So that's when the volcanologists said, well, maybe there's something going on before the eruption that we should know about. In fact, these big explosive eruptions come after years of repose, 200 years or so. So if the volatiles in the magma chamber were separating out and getting towards the top of the chamber, that would account for these explosive eruptions as the gas is released. And this explained a lot. Now that comes out of Tom's. In addition, aviation hazards were an issue. Jet airplanes had flown into volcanic ash clouds. Another interesting thing is we discovered a volcanic eruption by accident. In 1984, Mauna Loa was erupting, and Tom Cassadeval from the USGS called me from San Francisco saying, I'm on the way to Hawaii with a COSPEC instrument to measure the sulfur dioxide in the Mauna Loa cloud. Can you get us Tom's maps to show me where I should fly the plane? Well, we knew how to make our printer maps, and we knew how to measure total ozone. So that's what he did. We sent it out to him, and he was able to plan his mission based on those Tom's maps. Well, one of the orbits that went over Hawaii also went over the Galapagos Islands. And so I called up Jim Lure at the Smithsonian. They keep track of all the volcanic eruptions, and I asked him what volcano erupted. He said, well, there's no report of any eruption. And so he talked to the people in Ecuador, and they said, well, we'll go out to the Galapagos Islands, find out what's on it. So they confirmed our observation of this eruption about a week later. So another first. Well, the big eruption was Mount Pinatubo. And this really tested everything. The other thing we learned that we could do is we could use aerosol index retrievals from the TOMS data to measure ash. And so now here's an example of the two clouds measured with the same instrument, the sulfur dioxide cloud and the ash cloud. And now we could watch as the ash settled out and separated away from the SO2 cloud. And it's lent another dimension to our perspective. Another interesting case was the eruption of Mount Spurt up here in Alaska. We were able to capture the SO2 cloud day after day, and it ended up being sheared by when it merged, got it caught in the jet stream into this long banner, which then drifted as its own pattern. Well, it happened to be over Toronto, Canada, where Jim Kerr had been measuring column SO2 with a Brewer instrument. And so we were able to get a validation of our retrievals from that coincidence. And in fact, Meteor 3 Toms was also flying. So we got a validation of its SO2 retrievals at the same time from this one event. 25 years of SO2 mass. We can measure every volcano that erupted and over this time period. This is unheard of, never been done before. So here's a picket fence diagram of all the eruptions that we saw with the TOMS instrument, except for this annoying data gap between instruments. But all the big ones are there, El Chichon, Pinatubo, and so just a wealth of knowledge for volcanologists. Well, this field is all matured now, and so now we have websites that Nick is responsible for where all of the volcanic, the SO2 data, which has now been expanded with better sensitivity with the OMI instruments and OMS instruments. It's all now, this is a mature science, and it's was a real pleasure to live through these days when from the beginning of the first rocket measurements to the satellite and all of that, and watch this, just fascinating. So I won't go through all of these things, but that's the sort of thing we're doing. But I No, I didn't do it by myself. And there are so many people to thank for collaborating and helping and funding and everything. And this is just a partial list, you know. Starting with Ed Nye, and then Venke and Julius London, and Jim Hughes funded our rocket development. And these people all carried out the rocket development work. Don Heath, another key man, and Bill Nordberg and Bert Roeder, and as far as BUV development. Then there's Dave and Mateer, the two real heroes of satellite ozone sounding. Then, of course, my great friend Paul Crutzen, who also changed my life in another way. Then back here at Goddard, in meteorology, we've got Lou Uccellini, and we got Mel Shapiro. And then in the SO2 world, Lou Walters was the guy that found funding for us to develop the SO2 retrieval business. That was not part of atmospheric sciences. This came out of solid earth and volcanology. And Lou arranged for the funding. Meteor 3, Chuck Cody, John Liacino, Uli Hartman from Orbital Instruments now, Curtis Gordon, and then finally Nick Krotkov, and so many more. But that's my story.
So we can take a few comments or questions.
Kidding. Anyway, thanks for the talk. That was excellent, and it's a fascinating career.
Thank you, Ernie. Yes, we don't want to lose this old rocket data. In fact, any of the old data that has value, and so thank you for helping on the archival project.
Correct me if I'm wrong, but I believe the original Tom satellite had an expected life of 1 year, or a target life of 1 year.
I don't remember that number. I do recall that if you design for something longer than a year or 2 years, it's going to cost you lots of bucks. So chances are, you know, these things are artificially time-sized in order to meet a budget. So, you know, if you want to guarantee a longer life, that's where the real cost comes in.
How long did it last?
14 years. We made it, yes. Well, Beckman Instruments and those people made it. Right.